In this video, I'm planning on going over the integration on problems number 1 and number 2 for homework 6. And the reason why I want to do that is because on the homework, for the most part, everything was done really well, but the thing that a lot of people missed was this integration for, the integration for 1 and 2. So pretty much everyone had the problem set up correctly, but then a lot of people did the integrations wrong, and I made the same mistake, and so I don't know if this is my fault, because I showed a few people my answer, and so I don't know if that was the problem, or if you're just making the same mistake I made, which is just, so engineers have this problem of writing, basically anybody outside the math department, like engineers, physicists, etc., have this problem with writing their definite integrals kind of sloppy, and I'll get to that in a minute, but I think that this is what really caused the problem. So I just want to show you what I mean real quick, so because this is something that you want to be really careful with in the future as we continue to solve these problems. So for instance, in physics, this was probably one of the first problems you saw that involved integration. So let's say you have dv, so this is velocity, so the change in velocity with time is equal to acceleration. And so you can solve this two different ways. You can use indefinite integral, or you can use a definite integral. And so with the indefinite integral, if you remember, you don't have boundaries you don't have integration limits. So this would just be dv is equal to a dt. And so then if you integrate this, then you get v is equal to a t plus c. So then the c is a constant. And so the reason why we need this is because we haven't applied limits to our integrations. So then if you solve for c, you know that when t is 0, then your velocity is v naught. So then if you plug this in and solve, then you just get that c is equal to v naught. So then v is equal to a t plus v naught. And so this should be really familiar. Like, this is what you would learn in first year physics. So the other way that you can integrate this is you can apply the limits. So you can say dv, and this is from v naught to v, is equal to a dt from 0 to t. So this is what I'm talking about where things kind of get sloppy. Technically, this should be, so we have our variable of integration, and we're naming one of the limits as the same variable, and this is kind of sloppy because this is technically calling the because these are two different variables, and so this is technically calling two different variables the same thing, and so it's just not the best way to do this. And I think that this was kind of the issue in at least problem 1 on the homework, and so I'll point that out in a minute. But the thing is, so this should really be something like dv v naught to v1, and then this one, same thing, so 0 to t1 or t2 or tf, whatever you want to call this. But the problem is that pretty much anybody outside of the math department writes integrals like this. They're like this in the textbook, and so I don't recommend not doing this. I just think that you need to be really careful when you go through your integration. And so then if you integrate this, we know that this is just v, and then if we apply the limits, is equal to a t, and then same thing with this one, we need to apply the limits. So then if once we apply these limits, we get v minus v naught is equal to at minus 0, because a time multiplied by 0 is 0. So then this is just equal to v equals at plus v naught. So you get the same answer. And so the reason why I'm pointing this out, this seems really obvious. This is like first year calculus, but if I saw a lot of mistakes where people were solving it, like they were kind of mixing these or not applying the initial condition, or what the mistake I made was integrating this. So you had, like in our problem, we have 0 to tau, or 0 to t, and I integrated it, and then I just assumed that by applying this second limit of 0 that it would just be 0, because a lot of the problems we've been solving, that's been the case. And so then it just, I forgot to, I didn't get this initial condition because I just assumed it was 0. And so that was a mistake I made. But the other mistake that I think you can end up making with this, because when you have the same variable name here, so it would be really easy to say, okay, the answer is v, or, well, let's just say, well, coming over here, like, because this one actually is 0. So then if you just do your integration and you don't apply the limits, it doesn't matter in this case because you get the same answer, because if you just solved this and got at, then since this limit is named the same thing, applying it doesn't change your answer. And so it's really easy to just kind of skip that step and assume that whatever you subtract off is going to be 0, but on that first problem that wasn't the case. And so I think that this is, you just need to be really just be clear when you're doing your integrations. If you're doing them like this, then you need to add in your constant, and so just do that and don't assume the constant is 0, which is what it is. It has, in this class it has been 0 for most of the problems, but we got to a problem where it wasn't, and so then if you assumed it was, then you got it wrong. So, or if you're gonna do it this way, then just make sure that you put your limits in, or just make sure you go through and solve your boundaries. So this is really basic, but I think that a lot of people were kind of confused about at least problem 1, and I know that for problem 2 it wasn't this stuff, it was the integration factor that kind of screwed some people up. So I was going to talk about that one too, but I just wanted to make sure this was clear, because I think that a lot of times when you write your integrations like this, like 0 to t or 0 to x or whatever you're doing, it's really easy to just solve it like it's an indefinite integral and then skip applying the limits, because you're 0, when you apply the 0 it just comes out as 0 anyway. And so just be really clear. I would almost just start writing it down just so you don't get confused by that. So I'm going to erase some stuff and then do problem 1. I'm not going to do the entire problem because it's really I think that by now people, I don't remember seeing any that weren't set up correctly. So it was really the integration that a lot of people got wrong on this problem. So I'm just going to go to the final integral and then integrate. So where I want to start is this d cb, and then you had cb naught to cb, and this is equal to 0 to tau, K1A CA naught E minus K1A tau minus K1B d tau. And so this is another case where the upper limit is the same as your integrating variable, and it's kind of a slot. I mean, if you'll never see people do this in math, but like in the math department. But the thing is, if you're not in the math department, this is how everybody does it. So you just need to, I mean, I think it's okay. You just need to be really careful, because this is, I think that it was because of this. I think it's where this, so when you integrated this and you applied your 0, like you put your 0 in here, this doesn't come out to be 0, but I think a lot of people assumed it was, and that's what I did. And so I think that it's good to just write this, to write down everything as you're doing it, so then you don't get confused. And so if you integrated this, then you got CB, and then the limits were CB naught to CB. And CB naught happens to be 0 in this case. It's not always 0, so, but in this case it is. And then you have, so then if you integrated this, then you got minus CA naught E minus K1A tau minus K1B tau, and then the limits were tau to 0. So then applying these limits, we just have CB, because this is CB, I'll just put the whole thing in, CB minus 0, because CB naught is 0. And then you had minus CA naught E minus K1A tau minus K1B multiplied by tau. And so this is where I think it can get confusing, because you haven't, since you're using the same variable for two different things when you do this, you haven't actually changed anything in here, because now you're just saying, oh, well, this variable of integration is that, and so that's why it's easy to just say, oh, this is my answer, and then assume that the second part is 0. So anyway, this would be minus, and then you have minus CA naught, because e to the 0 is 1, minus 0, because you have K1B multiplied by 0. So then if you simplify this, you get CB is equal to, and this becomes a plus, so I'm going to have CA naught minus CA naught e to the minus K1 tau, so actually so I'm going to have CA naught 1 minus E minus K1A tau minus K1B tau. So then this is the answer. And you can see where if you didn't apply this, then you wouldn't get this initial condition. So, and then you can do this problem. The other way you can do this problem, and I'll just go through this real quick too, just so there's not confusion, because I think there was just a lot of confusion with this. So I'm going to erase this real quick. So the other thing you can do is just take these off, and then you're solving this as an indefinite integral. So then you would need to add in a constant. So if you do this, you get CB plus C is equal to, and then this one is the same thing, so minus CA naught E minus K1A tau minus K1B tau plus C. And I'm just going to combine these C's, these constants. I mean, this would probably be like C1, C2. I'm just going to combine these constants, so I have one constant, so then I would have CB is equal to minus CA naught e to the minus K1A tau minus K1B tau plus C. So then you need to solve for C. And so the way you do that is apply your initial conditions. So you know that at tau is equal to 0, CB is 0. So then you can say CB 0 is equal to 0. So then you can solve this, so you can plug in 0 for tau and set that equal to 0. So you get 0 is equal to minus CA naught multiplied by 1 minus 0 plus C. So then C is equal to CA naught. So then you can plug that in, and if you do that, you get CA naught 1 minus E minus K1A tau minus K1B tau, which is the same thing we got before. And so just be really clear about in your mind about how you're solving these problems, because I saw people mixing methods. I saw some that were like that did what I did, where you just kind of assume that the constant was 0, or that the lower limit set the entire thing to 0. So I know this is really basic, but just this I think that this is, at least for me, this is where I sometimes make mistakes, because it's like you're spending a lot of time getting the problem set up correctly and making sure that that's right, but then you don't pay as much attention to the math. So I'm going to erase this real quick. So for number 2, I'm going to once again start with the actual integral that we're or the differential equation that we're solving. So we had d CB dt plus K2B CB is equal to K1A. So the problem with this differential equation is you can't just separate and integrate like we have been doing. And so if you want to review this, I just have this calculus book, but this stuff is also online too. So this is, so you need to use this method using an integrating factor. And so if you look at, if you look at this equation, you can tell that it's in this form: dy dx plus px y is equal to qx. And so just looking at a few different equations, so this can look a few different ways. So say dy dx plus x squared y is equal to e to the x. So then in this case, px is x squared, qx is e to the x. Or you could just have dy dx plus 5y is equal to 2. And in this case, px is equal to 5, qx is equal to 2. So it can be, this px and qx, they can be a function of x, or it can just be a constant. So just as long as you can get your equation in this form, you can use this method. And so what you need to do is, I'll just step through the steps real quick so you can kind of see, and then I'll solve that. And I'm not going to spend as much time on this as I did in the video I did specifically on this, but just so that everything is here. So you solve for your integration factor, and what that is mu is equal to e px dx. And so then if you plug px into this equation and integrate this, then you get mu. And so then what you do after that is you multiply your equation by mu. So to do that, you end up with something that looks like this. So mu dy dx plus mu px y is equal to mu qx. And then if you remember by the product rule, you can rewrite this as d dx mu y is equal to mu qx. So then you can just solve. So you can integrate this and solve for y. So you have mu y is equal to integral of mu qx dx plus c. And so then if you solve for y, you have y is equal to 1 over mu integral mu qx dx plus c. And then, like we talked about before, you'd solve for c using your initial condition. So, and I always think that with stuff like this, it's easier to see how it actually works with a problem instead of all this stuff. So I'm going to solve this using this method. So I'm going to erase some stuff real quick. So using this method, the first thing we need to do is solve for the integrating factor. So we know that mu is equal to e px dx, and in this case px is that k2b, so then this is equal to e integral k2b, oh, and this is dt, so then this is, if we just integrate that, then that's equal to e k2b t. And in this case, when you're integrating when you're doing this integral for your integration factor, you don't need to worry about c. Like, you don't need to add c to this. So then if we multiply this equation by this, so e k2b t dcb dt plus e k2b t k2b cb is equal to k1a e k2b t. And then we can rewrite this using the product rule. And if we do that, we get d dt e k2b t cb is equal to k1a e k2b t. We can integrate this, so if we do that, we get e k2b t cb is equal to the integral of 0 to t k1a e k2b t. And so then, taking that integral, we get e k2b t cb, and that is equal to, so this is k1a e k2b t over k2b, and then applying the limits we have 0 to t. And so, like my previous example, the reason why I don't have plus c is because I'm applying these limits. Although you could still add c to this and it'll just cancel out, and I'll show you. So plus c, and then I have my limits. So then if I apply the limits, e k2b t cb is equal to k1a e to the k2b t over k2b plus c minus k1a e to the 0, so it's just multiplied by 1, so I end up with k1a over k2b plus c. And so then you can see that I'll end up with c minus c. So that's why, even if you add it in when you're doing when you're solving a definite integral, it'll just cancel out. And so I guess it's not wrong to add it in, but I saw some people where they didn't end up canceling this out, so then they solved this, like they basically came up with this equation, and then they tried to solve for c as well. And so just be really, this is why sometimes skipping steps with these problems is a bad idea, because you'll get confused. So just write this out. And so if we solve for CB, so if we divide this over, then we get CB is equal to K1A over K2B E K2B T E minus K2B T minus K1A over K2B E minus K2B T. And I'm just going to erase this real quick. So then I just want to pull out the, so first of all, that just becomes 1 because these combine. And then I want to pull out the K1A over K2B. So then I have CB is equal to K1A over K2B 1 minus E minus K2B T. And then that was the answer. And then this problem actually goes on, and you can solve it for, like, this equation is only valid if CA is present. So then if CA is not present, then you can continue and derive a second equation for that case. But I'm not going to go through that because I'm pretty sure he went through that in class. And then I'm not going to go over number 5 on this assignment because I went over that in class in pretty good detail, unless someone specifically asked me to go over it. And then I'm pretty sure that he went over problem 4 in class 2. So as far as the homework, it looked pretty good. It was just these integrations that I saw problems with. So that's why I wanted to kind of talk about that.